Alright, so so last time I just wrote down the action for the D brane and D branes on top of each other. So this was how you obtain the action for the gauge fluctuations on the D brane. And now I want to write down a different representation of the same object, which is essentially determined by how it curves the space-time around it. So this was the first thing. So let me just summarize what we did. An important point of last class was just that if you have n D branes on top of each other, and if you look at the action that describes fluctuations of the gauge field living on these D branes. I didn't derive this, but I'm just stating it. It's just it's given by non-abelian gauge theory. So if you have n D branes, n P branes, P plus one-dimensional objects, then it is described. These fluctuations are described by non-abelian gauge theory. I didn't tell how this UN gauge group arises, but you can think of it as follows. So suppose if you have n D branes like this, you can label them like 1, 2, 3, up to n, and then you look at these fluctuations of the gauge fields. The fluctuations of gauge fields are coming from the open strings. So these open strings have ends. They end on D branes. This is the definition of an open string. So you can label their endpoints. You have to distinguish these open strings. So you can label these endpoints of D branes by these numbers that are running from I to j, from 1 to n. Okay, so this is I, this is j. So in this case, this is n, 2, n, etc. And so since there are these fluctuations, these gauge fields living on them, they should be also labeled by these quantities ij. Okay? So if you look at now, if you put all of them on top of each other, there are all different kind of gauge fluctuations. So this is the gauge fluctuation going from 2 to n. There's another one going from n to n, 1 to n, etc. So all of them, all combinations. There are n squared different combinations. And so these n squared different combinations essentially gives rise to this UN gauge group living on the D brane. So the action that we obtain is something like the action of P plus 1 brane in the limit AdS becomes small. If you make the expansion and throw the constant term, you arrive at some constant of tension of the D brane and e to minus pi 0, let's say this is the integration constant that we were asking about. And then you have trace f squared. So this f here is f squared is f mu nu. And then you have to run, taking the trace means that you are summing over. So this is A, So this is non-abelian gauge field now. So you have to contract it with the and then you take trace. So these TA and TBs are the generating generators of the UN algebra. UN gauge algebra. So these I and J's, they correspond to essentially the indices of these matrices. Okay. So you obtain, I'm not deriving it, I'm just stating it, but I'm just motivating it, how it arises. So this is one representation of the D brane. You can represent the D branes in terms of these gauge theory. Okay. This is one representation. And if you are more careful and calculate what happens for the in string theory, there are objects called Dirichlet branes. Dirichlet branes. These Dirichlet branes are the objects actually that the open strings and on. And if you look at their action, again from string theory, you can derive their action. The same, I mean, you will obtain a gauge action. It's the same thing, but there are obviously some additional terms. So the D brane action, the D3 brane action, for example, we will be interested in D3 brane case. The reason that we are interested in the D3 brane case is because a D3 brane this is like a DT brane, but when T equals 3, it's a 3 plus 1 dimensional object. So the gauge theory living on them is a 3 plus 1 dimensional gauge theory. So we are interested in 3 plus 1 dimensional gauge theories. And for the D3 branes, what we obtain is as follows. So you obtain a gauge theory. Again, there is F square term with the appropriate normalization, etc. And here there is this tension term, D3 divided by the string that's coming from E to phi. So E to phi 0 is essentially giving the string in string theory plus other terms. So you obtain other terms essentially. What you obtain is an interesting theory. Is a theory that is called maximally supersymmetric Yang-Mills theory. So in addition to the gauge field, you have some scalar fields. So you have covariant derivatives of scalar fields. Now I'm replacing the index. I was writing A instead of this mu here. So that was FAD. Now I'm using F mu notation. Just don't get confused. So this is mu xi plus there are fermions lambda fermions d slash psi and there are some interaction terms of the form xi, xj, somewhere ij, something like this. So they're all in the adjoint representation. So these are all in the adjoint representation. Now don't write this. Let me write down the full thing. What we obtain is I will just mention it. What we obtain is an action for n equals 4 supersymmetric Yang-Mills theory. Yang-Mills theory means just non-abelian gauge theory. And so the full action is this.
So what is adjoint representation?
What is what?
Adjoint representation.
Okay, adjoint representation means that under the transformations of a gauge group, they transform by the commutatives instead of like you know what the fundamental representation is, right? So if you have a field under the transform, and if there is a symmetry, and if this is the representation of that symmetry of this group, then what you usually do, I mean, for the fundamental representations, what you do is that you write down this ij, yj, right? So this is how you transform it. But this is for the fundamental representation. For the adjoint representations, the adjoint representation is the representation that these generators themselves transform on. So this, so an adjoint representation of an object which has an adjoint index A would be something like dB commutator size C. Contrasted. Let me write it like with an epsilon, well, with this way. I will explain what this is. It will be like this, and this object is called. It is just a generalization. It's just a collection of constants. It's an antisymmetric under this exchange of indices. It's called the structure constant of the gauge group, and it is defined as depending on if you have a compact or non-compact gauge group, etc. In the non-abelian gauge groups that we have, it is defined like this. So this is the definition of the gauge algebra. Okay. For SU2, for example, these indices are just epsilon ijk. So in the case of SU2, what you have is sigma A, sigma B, the Pauli matrices, I epsilon A, B, C, sigma C. But this can be generalized to arbitrary non-abelian gauge groups. In case of SUN, this is the structure concept of SUN. So this is just this defines the algebra. And the objects, like the fields under adjoint representation, transform precisely like the generators themselves. All right. So this is what you obtain. I mean, this what I'm writing down is like the Lagrangian of n equals 4 super Young's theory. You heard about a different theory that comes close to this one, which was the n equals 2 super Young's theory. That is what Sara Pasquetti talked about. But now this has even more supersymmetry. This has n equals 4 supersymmetry. Don't worry about all the details of the theory, but I think in electron AdS CFT, I think it's a good idea to write down all this action in tubularity that just convince you that there exists such an action, which is the maximally supersymmetric action that you can write down. Everything is completely fixed in this Lagrangian that I'm writing down. You have a similar term for. So this field this is the gauge field. Again, there is a gauge field, but there is a different combination of the gauge field, which is a topological term. It's called theta term. There is this is in the same supermultiplet. Everything is in the same multiplet, supermultiplet. So by some supersymmetric transformation, you can relate all of these fields to each other. This is called the gaugino. This is the supersymmetric partner of the gauge field. So this is gaugino. These are the scalar fields that has some kind of cover term like that, and then there's another kind of. This is just the Hermitian conjugate of this. There is J. These are just some constants. I'm not going to write down these constants. That will not be very important. This is just a complex conjugate of gaugino. And in the end, well, there's another term, E squared, sum over ij. The commutator of its I and xj squared. This is the potential term, the quadratic potential for the scalar fields. Did I write everything? Okay, anyway. So the point about this action is that this is an action that you obtain from by studying the fluctuations of the D branes, D3 branes. And there are addable fields. I mean, first of all, the most important piece will be this one. First, this is just the gauge kinetic term. But then there are additional fields, all in the adjoint representation. They transform like variables. Now, so this. Let me just keep it here. It's not well. Now let me mention some important fact about this Lagrangian. So all of these constants here, this g, these constants, etc., in a normal quantum field theory, like this one, once you write down a classical action like this, and if you put this action in the path integral, and if you calculate the corrections, okay, so you can write down the corrections, but you can calculate, for example, corrections to the gauge coupling constant the way that Alto explained. I mean, if you consider, for example, this gauge, the coupling constant to the normalization. If you have an A mu, etc., then adjoint index. So this diagram and all the other diagrams that couple to it, for example, here there's inside this, there is these gauge fields as well. These are the covariant derivatives with respect to the gauge field. So they also couple to the x field like that. So you can have a diagram like this where you can have a diagram like this where the fermions run. And you can have diagrams like XX, so you can have something like this where X fields coupled to the gauge field, etc. So if you add all of these diagrams, what you find is that the sum of all of them is 0. Not only at one loop, but at every loop. Which essentially means that the coupling constant doesn't renormalize. So this is an extremely symmetric Lagrangian. This is constructed in such a way that it obeys the supersymmetry algebra. So these supersymmetry transformations relate all these diagrams to each other, but with some minus signs. So for example, if you start with this diagram and apply some supersymmetry transformation, you arrive at the same diagram, the same value, but with a minus sign. So they all cancel each other. So I'm not showing this here, but I'm just stating because to show it will take me 1 hour. But the claim is that if you have a Lagrangian like this, that is called N+4 supersymmetric Lagrangian, Young's theory, then none of these quantities, neither those constants nor these coupling constants G, they don't change as you correct the theory by including these parametric terms. And this is also true. It turns out that this is also true. So the Lagrangian is, it doesn't renormalize. So the statement is this N+4 super N is exact. It's quantum mechanical, it's quantum exact. By quantum exact, I mean that its beta function is 0. Now you know what beta function is.
Not real.
You know what beta function is? Everybody mentioned, but nobody wrote it down, right?
Yeah.
Okay, so this is the glorious moment of this class, of this school. So the beta function is the following. If you have a coupling constant, beta function describes how the coupling constant runs as a function of the energy scale. So you have to define the theory with some cutoff, or at some certain energy scale. I mean, to remove the cutoff dependence, you have to renormalize the theory, and then in general, this coupling constant becomes a function of the energy scale. And so this is the beta function describes how the coupling constant depends on the energy scale mu. For an example, for QED, how do you calculate that? So I'll explain how to do it in QED. Right? So in QED, for example, you get additional terms, but that are positive. So the contribution, the correction to the the coupling constant that you obtain from a diagram like that turns out to be positive. So in QED, the beta function looks like this. So in QED, beta function is positive. At 0, it is 0. But then it rises. In QED, when you compute this, what you find is something like GQ, blah, blah, blah.
Why we differentiate it with respect to the
It's just to define how it changes as a function of energy scale. I mean, if you're asking me why this is low, it's just for convenience. Naturally, the log appears if you do this calculation. So this is right. So the coupling constant. I mean, I can write down how the coupling constant changes, which is a solution to this equation, as a function of log mu. And it's if you start from an example, well, it is positive, so it increases. This is in QED. QCD, it's as you change the energy scale, log mu. It's like it's just the opposite. This is QCD. This is because, as Alto mentioned, there are these corrections, like there are these corrections, and also there are loop corrections where the gates will couple to each other. Here also there are these loop corrections, by the way. I just forgot to put them. Like this is the gauge field itself, the Gluino fields. And they make it some kind of run in the opposite direction. But in this particular theory, when it was for superionis theory, it just doesn't change at all. All these diagrams head up to 0 at every level. And what you find is that G is a function of log mu. It's just it's a constant. If you start at some point, it stays at some point. So it's just a parameter of the theory. It's just a parameter. If you write down the action like this, and if you go and do the path integral, it's exact. It's quantum mechanically exact. So it's just a constant. So this is important because this means that this theory has a very important symmetry property. Well, first of all, you realize just by looking at the action that there is no mass term. So there is no term that has there is no dimensional term. There is no dimensional coupling constant. This is dimension 0. This is dimension 0. Everything is dimension 0. There is no mass term, for example. So if you make a scale transformation, if you change your energy scale, mu to lambda times mu, okay? Classically, nothing would change because the action is invariant under. It doesn't depend. None of the parameters have dimension of a mass, so or energy. It doesn't matter. They are the same thing. So these parameters would stay the same. The same is true for QCD, of course. In QCD, if you write down the action of QCD, you have the same thing, the same structure. You have this plus fermions, but they are not in the adjoint representation. They are in the fundamental representation. Those are the quarks, etc. But still, you don't have any mass term that you write down in the big one. In QCD, you do. But suppose that I put all these mass terms to 0. Then QCD classically also would be invariant, but its beta function will still be non-zero if you consider these corrections. But in this theory, the beta function is 0, period, for non-perturbativity, completely 0, which means that the scale invariance here is not broken. So this theory is a version of QCD, something like QCD, but with exact scale symmetry. Let me write it correctly. Okay, so scale invariant exactly, or scale invariant. Yeah. Okay. So N+4 superior is the scale invariant theory. Do you understand what I mean by this? is this clear what I'm trying to say? But there are two different things that I mentioned. One thing is that an action that you write down may not be invariant under this transformation. If you have a parameter that depends on that has this dimension of a mass, for example, a mass term, and if you have m squared pi squared over 2, which this doesn't have. This is a parameter that has dimension. And under this transformation, this has to transform because this is a scale transformation. I'm changing the way how I'm measuring the mass or the length, whatever. But this is classically invariant. But on top of that, it is also invariant quantum mechanically because none of these parameters run by the end of the scale. It could have been secretly breaking the scale invariance if you consider additional corrections to these parameters by looking at diagrams like that. But this is also zero in this case. So it is exactly scale invariant. This is the only example that we know. There are different, some kind of deformations of this theory, but this is the only example that is scale invariant quantum mechanically in 4 dimensions. We cannot prove this, of course, but this is the only example that we know. So,
is it the only case n equals 4?
It crucially depends that you have a maximal supersymmetry. N equals 2 theory, for example, runs. Sorry, N equals 1 theory runs. N equals 2 theory is not, except in certain cases, it's not scale invariant. This is the only example that we know that where the weight function is exactly 0. Okay, so this is something that we obtain from D3 branes. These branes in string theory. Now I wanted to describe a different representation of these D branes that depends on that gives rise to the general relativistic representation of them. And here it is. So the second representation again, I consider the same situation. Let me recapitulate. So we started with this, and then obtained on top of this. I take the limit LS going to 0, and I obtained the n equals 4. I didn't obtain, but I just mentioned n equals 4 super Young's. I just motivated supersymmetric Young-Mills theory, gauge theory. And now, but also these objects, they have a different representation in string theory because they curve the space-time around them because they are massive objects. So you can also find as I was answering your question, there are two sides of Einstein's equation. You can look at the other side where to describe how these objects curve the space-time around them and what kind of curved geometry they correspond to. And then you can find, and the way to find it is as follows. So I will derive it for you. So suppose that I want to describe the geometry, the curved space-time geometry that corresponds to these D branes. What do? I need to solve Einstein's equations. But Einstein's equations are a little bit modified because these are Einstein's equations that come from string theory, not just pure gravity. But in string theory, as I mentioned, there are additional fields. So you have to write down action also for these additional fields that we have in string theory. Wonder if I wrote it down somewhere. It should be here. So, as I said, the action for GR was this. In string theory, instead of this, what you get, effective action for string theory is the following. So you get, string theory doesn't have any additional parameter. Everything is fixed in terms of string length scale. So all of these coefficients, etc., are fixed. What you get is something like this. This is the string length to the power 8. This string squared is just the expectation value, as I said, of the dilaton field e to phi 0. And then you get something similar. This is superstring theory in 10 dimensions. This dilaton thing appears there, coupling R. So you again have the same thing here, but it's corrected by this appearance of the dilaton. This is not going to be a problem for us because in our case the dilaton will not be a function of R. In the solutions that I'm interested in, these solutions, the three-brane solutions, this dilaton is just a constant, so it doesn't matter. I can set it to 1. And but there are additional terms. So there are like this running kinetic term for the dilaton, blah blah. This will be 0 in the case that we are interested in. And then there are some generalizations of gauge fields in higher dimensions. So by this, what I mean is E plus 2 is D mu A, D mu 1, A mu 2, blah blah, mu plus 1 minus 1. And this is measured in all instances. So these are some generalized gauge fields. And so the normal gauge field that we were talking about were one-dimensional, but these are P plus 1 dimensional. So this is the 10-dimensional action for string theory. There are additional corrections. There are other fields, etc. But these are the interesting fields that we will talk about.
Is dilaton masses?
Yes, dilaton masses are probability. It's in the same supermultiplet as the graviton, so it cannot be. Okay. Now, how do I find a solution to this complicated Einstein's action coupled to other fields that corresponds to this situation? So, what we have to write down an ansatz for the metric. So, what I want to find is the metric. So, what is G mu of ND3 branes? Well, you know the symmetries of the situation. For example, here, if you have ND3 branes and flat D3 branes on top of each other, we know that there are some symmetries of the corresponding situation. So there's Poincare parity, there's translation invariance along the D branes. If the D brane is 3-dimensional, I should have 3 plus 1-dimensional Poincare invariance. Am I clear when I say Poincare invariance? Do you know what I mean by Poincare invariance? Boost and translations. You just Lorentz transformations and translations. And in addition, there's isomorphism around. Well, if you take these D branes and rotate them, you should have some kind of symmetry. This is just like this is just a generalization of having a point-like particle. If you have a point-like particle, there's no translation invariance. This is 0. but then you have isometry around. So you have exactly the isometry in the transverse directions. So here you should have some isometry also. I mean, sorry, isotropy, what I'm saying, isotropy. So rotational invariance. So then you can make an ansatz for the metric. And the ansatz should be of this form. There can be some arbitrary function h. That may explain what I wrote down here. So this is the term, this is the piece. I'm writing down an action in 10 dimensions. This is a 10-dimensional curved space. So this is an action in 10 dimensions. So this part corresponds to the invariance along the d-planes. So these are the directions along the d-planes. Time direction and 3 space directions. x1, x2, x3. Let me call it x, y, z. X, y, z, and by x3, by this I mean dx squared plus dy squared plus dz squared. Okay, so all 4 of them are here. And then I require isotropy, and that gives me the transverse piece. So this is the transverse piece. Just like in the point-like particle, you can represent the space around it by some radial coordinate plus some angles. Right? So this is the isotropic way of writing it. So the generalization of that is just you still have the radial variable r, and you have in this point-like particle you have a 2-sphere. Instead of 2-sphere, here you have 5-sphere, because the transverse space is 6-dimensional, which is described by a radial coordinate and the angles living on the 5-sphere. Okay. So this is like the spherical coordinates. Right. So then there can be some arbitrary function that depends on this variable r, because that doesn't break isotropy. It's still isotropy, but it can change. If this function was just 1, if it were just constant, then the metric that you will obtain will be just a flat space in 10 dimensions. Because this is just a flat space. This part is flat space in 6 dimensions. This part is flat space in 4 dimensions. And in total it will be just flat space in 10 dimensions. But this function actually is the most important thing. And this function describes how the curvature of space-time arises. So how do you find that function? Well, you take this action. This is an ansatz for the metric. Okay, so you know what the metric, so the metric is given in terms of this function h. You plug in the Einstein's equations that you obtain from here, and then you solve the equation solution. So again, I'm not solving it for you, but I'm telling you how to do it. So once you have this action, once you have the ansatz is completely fixed by. Okay, it's not completely fixed. You can ask me the following. You can say, well, why these are not 2 different functions, for example? Why this should be just inverse of the other? Then I can put it in this form always by making some coordinate transforms. So this is in a particular coordinate term. I can always change my coordinates r, for example. I can redefine my coordinate r in such a way that this is just inverse of them. So that doesn't restrict the generalization. It's still without loss of generality. I can put it in that form, and then I have to solve the Einstein's equations. And you find the following. So you find that h is 1 plus r4 divided by r4, where this r is r4 is 4 pi gs LS8, N is the number of D3 branes here. And in this geometry, N appears here as an integer inside this constant. This is just a constant. Okay. This string is just a coupling constant of the strings. LS is the string length. Those quantities, those parameters, just were in the action that obtain our equations. And N is essentially the parameter. Is an integration constant in some sense, which is described as part of the solution. So this is the solution. It's a very simple solution. And this is the action. Well, this is the metric when H is like that function H is like that, like this. This is the metric for the D3 branes. Okay. Okay. So now I have two different kind of representations of the same thing. In the first situation, what I had was that now let me arrive at AdS CFT duality from this. So this is the second representation. The first representation was just the Young's theory. So two representations of the same thing. We have these D3 branes. So one thing is that, well, first of all, these D3 branes interact with each other. And this gives rise to the Young's theory representation. I drive this already. So Young is here. But not only that, there are also closed strings around. This is a string theory with some D branes. There are open strings that couple to the D branes. There are closed strings that are floating around, but they also interact with these D branes. So the action that you should write down for this is the action of the Young's theory. I already derived it. So this is coming from these open strings. Action for the Young's theory plus action for the closed strings in 10D flat space. Flat space because the space around is flat in the first representation. I'm coming back to the first representation that we had, plus some interaction terms. So these interaction terms come with the coupling constant that is G Newton, proportional to G Newton. And G Newton in string theory is completely determined. I mean, I wrote it down before I just erased it here. G Newton is the gravitational coupling constant that appears in front of the gravitational action. And in string theory, this was just, what was it? It was GS square LS to 8, yes, and some additional terms that depend on pi, like 2 pi to 7 or whatever, but it's not important. So the important thing is that G Newton is proportional to LS. And I'm interested in the limit, in the point-type particle limit, where I can replace all these strings living on the D branes with point-type particles. That gives rise to the Young's theory representation, the gauge fields. And this G Newton goes away, so I can get rid of the interaction term. So I arrive at, this is the first representation, I arrive at Young's theory in 3 plus 1 plus closed strings living in 10-dimensional flat space. Now the second representation, which is this, with this function here, I just want to take it to 0 to see what I get. You don't have to, but I just want to take it to 0. The reason that I want to take it to 0 is the following. So as I said, these are open strings living on the D branes. So an open string has a lot of fluctuations. So this, first of all, you can write an open string, fluctuation open string, as a rigid string plus fluctuations on top. 1 fluctuation, 2 fluctuations, blah blah. Okay? So all of these fluctuations comes with the factor of L string or Helsinki square, essentially. So because this corresponds to zero mass, there is no mass here. This corresponds to a fluctuation with some mass that is proportional to LS, let's go by LS square. Okay, this is 2 over LS square plus blah blah blah. So the zero mass particles that are in this situation, that describe this situation, are you can look at by looking at these fluctuations of open string. You can count what they are. So they include this gauge field A. This is the gauge field that I'm interested in. I'm interested in describing the physics of this gauge field. Okay, this is what I want to do in QCD, for example. But then on top of them there are these stringy fluctuations. But if I take the limit Ls goes to 0, all of these string fluctuations, their mass becomes infinite. So they become non-dynamical, they cannot move. So I can ignore all of these string fluctuations. So what I end up with is just the vacuum state of the theory, the massless state of the theory, which is just described by this Young's theory, as I explained. Okay, so this is the way to arrive at Young's theory. So I am interested in the limit Ls goes to 0. So this is what I would call the low energy. This is what the low energy means. Low energy. Okay. So, but at the same time, we are lucky enough that this interaction terms also go away, and you arrive at this representation where you have just pure Young's theory of this n equals 4 super Young's theory, whatever, with some plus these closed strings. But this is the second representation of the same situation. And in this case, H was just 1 plus R4 over R4. I can erase this.
What was the thing that these corrections correspond to closed string corrections? What do they correspond to?
They correspond to some interactions with, you see, these objects coupled to open strings. The open strings hand on them, but they also interact with the closed strings. So closed string can interact with them. So I mean, a D-brain is like a sheet like this, and suppose this is a closed string, so it can interact with that. So, but if I take this limit, these interaction terms, this interaction coupling constant goes to 0.
Okay, and the other term, the tiny strings.
This tiny string is essentially these things. I mean, they don't see each other. So on the same space-time, there are these objects.
They have some physics difference because we have an extra.
Yeah, they have some physics. Yes, they are just in closed strings living in n-dimensional flat space-time. So they can interact with each other. They can fluctuate around, blah blah. But I will not be interested in this because this factor will cancel out. You will see. Okay, so in the second representation, what I have is this geometry, this curved space-time. Which is given by this geometry, and if you plot it, I will just give a schematic plot of this geometry. It looks like so. It is as r goes to infinity. So this is your radial variable that describes how far you are from these D-branes in a spherical geometry. As r goes to infinity, this vector goes away, then h becomes 1, and you arrive at the flat space-time. So you just asymptotically, the space-time becomes flat. So it's very curved, just close to the D-branes. So this is the r equals 0 point. Very close to the D-branes. Your space-time is very much curved, so this h is very big. But as r goes to infinity, the space-time becomes flat. So you have, the geometry looks like this. So you have something like an asymptotically flat space. So what I'm plotting here is that suppose that this is like a trumpet, okay, so it just opens up. So it just there's this piece that is bigger. suppose that this is like a trumpet, but then it opens up and becomes flat completely. It goes to infinity. Okay, so this is an opening. So this deep-range geometry looks like this. So this is the limit r goes to 0. This is the limit r goes to infinity. As r goes to infinity, this space-time becomes flat, but as r goes to 0, this is the radial direction r. So these are all the transverse directions that you have there. And there, in the r goes to 0 limit, it just becomes extremely curved. And the nice thing about this is that if you, so in the second representation, what I have is just, there are no deep ranges anymore. So I replace the deep ranges with the geometry. I have no deep ranges. So I only have closed strings in this curved background. There are no open strings there. Because open strings are around only if there are deep ranges. Open strings has to end on some place. Otherwise they need to be open. They have to end on some place, and if there are no deep ranges, then there is no open strings. So it's only closed strings. Closed strings on the deep range geometry. And you can, roughly speaking, divide this geometry into two parts. In the throat region, this is called the throat region. This looks like a throat. And the flat region. Now, in the closed strings also we have all kinds of modes. So as I was explaining for the open string case, in the closed strings you can also think about closed string as a rigid object plus fluctuations, plus one fluctuation, plus two fluctuations, etc. So this corresponds to the vacuum of the closed string, where you have these, in the vacuum state, these are massless, so these are string-like excitations. But these are massless excitations. And for the closed string case, there are two different kind of, there are different kind of massless excitations. One of them is G medium, the graviton. The other is E medium, called Brahm's field. The other is the dilaton. And that's all. You don't have more. And there, this corresponds to stringy states, whose mass become infinite if I take the limit LS goes to 0. So I don't care about these string excitations in the limit that I want to take. Alright. So in the limit that I want to take, what happens is that what you can show is that there are two things. First of all, you are only left with these massless fields. Okay, so in this limit, in the low energy limit. First of all, there are only the massless fields survive. Second of all, these two different regions, the flat region and the throat region, decoupled from each other because of the gravitational redshift, this Doppler effect that I was talking about. So if you have an excitation here, if you just try to see how it moves, it loses its energy in such a way. If this excitation is with some frequency, say omega, okay, you can show that in the limit LS goes to 0, in the limit where this throat region becomes extremely curved, so this the absorption cross section of an object with frequency omega goes like omega to 4. And in the low energy limit, where omega goes to 0, this goes to 0. In the limit that I measure the energy of these excitations, the length scale goes to 0. So the way I'm measuring these excitations also goes to 0. This goes to 0. Like the absorption cross section goes to 0. And what you arrive at is that these two regions completely decoupled from each other, and you have a particle. You can, like physically, you can think of it as follows. So if you have an excitation like this, with some frequency omega, there's huge gravitational redshift, so it cannot really climb this gravitational potential. Okay, so it loses its energy as it tries to climb up. Similarly, if you have an excitation here in the flat region, its wavelength is so big that it cannot probe this small region. It cannot just go into that small region. Okay. But this is what I mean by absorption cross section goes to zero. Absorption of an object living here at this point goes to zero, or the probability that this object will climb up the gravitational potential and become free in the flat region also goes to zero. So then you arrive at the second representation of the same thing, the same physics, which is just the physics. Yeah.
Are we talking about the probability function of graviton or any other different type of waves?
You can do. I mean, you can calculate, for example, the 2-point function of the graviton, or a propagator of the graviton from here to here. I mean, these kind of quantities you can calculate, or some arbitrary excitation at some frequency omega. Those are quantities that you can calculate. I mean, these quantities like the absorption rate, something like that. Absorption cross section. So these quantities are calculated in, for example, in gravitational physics for black hole backgrounds and things like that. So people do this kind of. Okay, so when you calculate, for example, gray body factors, it's like that. Okay, so the second representation is the following. I will give a break, like 5 minutes break in 1 minute. Let me just write down what I have in, let's say, 3 minutes. So what I have is that there are two different physics on the skirt geometry. One is the throat region, closed strings in the throat, plus closed strings in entangled flat spacetime. Okay. This is the second representation. The first representation was, let me remind you, Super-Yang-Mills theory in p+1 dimensions. This was coming from the open strings, living on the brane, plus closed strings in 10D, flat space again. These should be the same thing. I didn't change anything. They are exactly the same. They describe the same physical situation. There are two completely different representations of the same physics. So they should, I mean, the actions that you write down, the first action should be equal to the second action in this limit, in this low energy limit. So then you arrive at the fact that you can remove these closed strings in flat spacetime, and you can just state, well, this is very hand-waving, I agree, but there is no other way to arrive at AdS utility. That's why it's called a conjecture rather than proof. You can state this, and then you can calculate and check if this works, and it indeed works. And this is just motivational. So what we arrive at is the action for the Yang-Mills theory, and it's possible supersymmetry, equals closed string theory in the throat region. Of the brains. Brain geometry. So what is this throat region in the D3 brain geometry? I just erased it. That was just, remember that the metric was, what did I write here? H1 half or H minus 1 half?
H1 half.
H1 half. H was this 1 plus R4 over R4, 1 half, minus D squared plus V square. So this is like dx square plus dy square plus dz square plus 1 plus r to 4 minus the half.
The first one is minus.
Yani hiç olmazsa hadi böyle.
Okay. The r square plus r square the omega 5 square. Okay. The throughout region corresponds to, as I said, corresponds to this r goes to 0 limit. If you take the r goes to 0 limit of this metric, you can ignore, this becomes very big, so you can ignore these ones. You get rid of that. And what we arrive at is the following. So this becomes in the limit, the throat limit, which corresponds to the low energy limit. This is what you get. So this the first one is like r to minus half, just r square plus plus the r square over r square plus r square the omega 5 square. You agree? This part is called the 5-dimensional antidecimal space. This is the metric of the 5-dimensional antidecimal space. This is AdS 5. This is the 5-dimensional sphere S5. So what you have here is closed strings in this curved background closed string theory on AdS 5 times S5. Okay? So this is the statement of AdS CFT duality. It just says that this particular theory, N equals 4 square IMS theory, is the same thing as the closed string theory on this curved background. You don't know either side, but there you go. So okay, let's give a break for like 5 minutes, but not more. I can do two things. I can continue, or I can give you a break if you have time already. Break. Okay. Any questions? It's very clear, right? It's very intuitive. Like this is this N equals 4 square IMS theory. Of course, it should be the same thing as close to AdS 5.
Coupling constant and LS.
Yeah. It all only depends on this.
T-square'ler falan ne oluyor? T-square'ler ne oluyor? Dekoratif.
DT kare.
İnterferensi.
İşte bak şeyde class space metriği nasıl yazıyorsun? Minkowski üzerindeki eksi DT kare artı. Nasıl yazıyorsun?
So this is the last lecture. You will be completely free after this hour. Don't worry, it's just 1 hour left. And so I just stated what AdS CFT is, and it just relates thanks for superunion theory, which is just a gauge theory living in 4 flat dimensions, 3 plus 1 dimensional flat space, with a type 2B string, well, closed string, some closed string theory, living on this curve and here background, AdS 5 process 5. Now, so this is why is it helpful? And so this theory is a I mean, this statement is in some sense relating the full quantum mechanical system with some another quantum mechanical system. String theory is a quantum mechanical system, and Yang-Mills theory is a quantum mechanical system. We don't know how to solve Yang-Mills theory exactly. We don't know how to solve closed string theory on this curved space-time exactly. So, this kind of statement is why is it helpful? So the reason that it is helpful is the following. There is a particular limit, a simple corner of the AdS CFT duality. By the way, the reason that it's called AdS is because of this AdS. So this is AdS. And this theory is CFT. As I said, it's a scale invariant quantum theory that is called conformal field theory. So this is CFT, this is AdS. The name AdS CFT duality comes from this. So AdS CFT duality, sometimes called correspondence, it's the same thing. It's following corner. So let me relate the parameters in both cases. So here we have 2 parameters. This is the Yang-Mills theory. So it has a coupling constant G Yang-Mills that I denote as G. I will keep the same as G. And then there is it has a symmetry. Sorry, it has the gauge symmetry, SUN gauge symmetry, or UN, whatever. The U1 factor. It's not very important. Let's take UN. So from here, n is another parameter. In our case, it's fixed. It should be an integer, but I can take it as a parameter. And here, what I have is the G string and S. Okay. And these parameters are related to each other. You can see how they are related to each other by comparing the, for example, in the D brane action, what we had was there was this 1 over G string that was sitting in front of the D brane action. Right? So it came from e to minus 5 that we had. Right? So this is an F squared term. So this e to minus 5 gave rise to G string. And now if you want to write it in the usual way that we write the Yang-Mills action, instead of this G string square, what we write here is the Yang-Mills square. So then I was calling G squared. So this is the action for the Yang-Mills theory. So in the previous action that I wrote, and it was for super Yang-Mills, I wrote, I think I used a different representation of the same thing. So you can obtain this by just changing values A to A or G. Anyway, so this is the Yang-Mills side, this is the D brane side. So G string should be the same thing as G Yang-Mills squared. Okay, let me put Yang-Mills squared. So this is one relation. The other relationship comes from, so it involves N, and it comes from essentially by looking at the action for the closed string theory. So there we had, okay, the action for the closed string theory has this F. You see, what I wrote there was something like this, right? E to minus phi r minus that phi squared plus blah blah blah plus I wrote Fp plus 2 squared. So in this case, P is 3. So it's an F5 term. So this F5 term is just a 5-point field. It's like the generalization of a gauge field, but not with one index, but with 4 indices. This is the field strength for that. So F is just D, A, mu1, mu5, mu1, A, mu2, mu4, and so on, right? So these D3 branes, just like an electric field, which is described by this gauge field A mu, couples to a point-like particle like an electron. These D branes, these D3 branes, couple, these are just 4-dimensional objects. And instead of coupling to an object with 1 index, they couple to an object with 4 indices. So the kind of electric field that it couples is 4 indices, mu1, mu4. And then the electromagnetic theory that you would like to write down for this electric field, this generalized electric field, has 5 indices. So this is, you don't have to worry about it very much, but in string theory there are all kinds of generalizations of the concepts that you know from usual electromagnetic fields. So this is a 5-form field. And this 5-form field, just like the electric field coupling to the electron is the strength of the electric field. The field strength of the electric field is proportional to the number of electrons that you have. Just if you have like 1 electron, and if you surround it by Gauss's law, you obtain that the field strength should be proportional to E. Right? So in this case, we have n D3 branes on top of each other. So if you look at the field strength F5 that is surrounding these n D3 branes, it should be proportional to n. So the number of D3 branes, so integral of F5 on this 5 sphere that is surrounding this D3 branes is it's some constant that I don't worry about now, times n. This counts the number of D3 branes inside. This is just generalized Gauss's law. Okay. And at the same time, since I'm solving this action for this Einstein's theory action, in Einstein's equations, if you look at the Einstein's equations, remember we had G mu nu equals to 8 pi G Newton T mu nu, something like this. The equation of motion, the Einstein's equation that you will obtain from this, forget about this. This is just a constant. I don't care about that. In this solution, this is just a constant. Phi is just phi 0. It's a constant that I can set to be 0. This is not there. So what I will get is like this would give rise to this term with the square root of G, of course. This term would give rise to G mu nu. And these other terms, you can treat them as method. These are just like method. So this is like electric field that we have that gives charge. This is like some scalar field, etc., which is 0. So this is not there. So what I have is that from this equation, on this side, I have the field strength of this. So the energy momentum tensor of this generalized electric field. So what I should have here is that this should be proportional to n squared, right? Because the energy momentum tensor of the gauge field is quadratic in f. Yeah, so this should be proportional to n squared. And the curvature of spacetime, so this is just the curvature of spacetime. The curvature of spacetime is given by, you can calculate the curvature of spacetime. You just take this metric, calculate the curvature. I mean, you can calculate this tensor, right? So this tensor was r mu nu minus 1/2 r g mu nu. You can calculate what these things are. Given the metric, you can do that. And this thing will depend on this quantity r. That is your integration constant. So this relates n squared here with this r squared. So what is r? R was given in terms of G string, and can you remind me what that was? G string squared.
4 pi is LS times
LS to A?
I
Okay, so this is a relationship that you will obtain. But I'm worried about something here. That this should be 4. Right? I mean, it should be the same dimensionality. Okay, maybe I just LS to 4. It's just LS to 4, not 8. Okay, so this is R. From which you essentially you can arrive at a relationship from this equation that relates n to the curvature of space-time. And what you get is something like this. If you calculate the curvature of the space-time, the which is scalar. I just don't want to erase this, so I will erase this. So I have two things. I have GS equals GMX squared. And I have this relationship. Okay. Now so this is the relationship that I have. Now what I want to do, so this tells me how the string coupling constant is related to the coupling constant of Yang-Mills theory. This tells me how the curvature of space-time is related to the number of colors, right? So this is the relationship. These two describe how to relate these two coupling constants. So to different sides of the duality. Now what I want to do is to take a particular limit. What I want to do is the following. So I want to take the limit that is called the tooth limit. So the tooth limit is the following. You take an SUN gauge theory, and then you take the limit and goes to infinity. And in this case, it simplifies. Some simplifications. If you calculate, for example, Feynman diagrams, only certain kind of Feynman diagrams survive in this. I don't have to go into details in this, but it's just called the planar limit. So Wolfgang already talked about this, I think. This is called the planar limit. But I'm not interested in the simplifications on the field theory side. Instead, I'm interested in the simplifications in the string theory side. And what happens is the following. So in this case, I can get rid of all this. I mean, all the argument that I tried to give here was to end up with this relationship actually that I already had. So that was not very useful. These two equations are the most important equations that relate to two sides of the duality. And so what you can do is the following. So you can define what Tooth did was to define a new coupling constant that he called lambda. Okay? which is given by G square times n. Okay? So he considered the large n limit where he put n to infinity, okay, G to 0, but this is kept constant. This is called the limit. In this limit, you can think that there are no interactions there, because the is going to 0, but it's not true. Because if you make perturbative expansion in the limit n goes to this number of colors close to infinity, the effective coupling constant that you have, that is counting the number of interaction points in the Feynman diagram, is given by this new coupling constant lambda. So what you have is that this coupling constant is kept fixed. N goes to infinity, Gn goes to 0, we have a simpler theory. And in here what happens instead is that now you can write
What if we said that Gn is constant?
yeah, it is constant, but it's a parameter of your theory. You can take it to be 0. It doesn't run, it doesn't change the function. This is not a change. This is why I'm taking it by hand. It's not a function of the energy scale. It is a constant, but it can be whatever you want. In this case, I'm taking it to 0. I am multiplying it.
I thought that when n goes to infinity, the n was going to 0, and it changed.
No. This is your parameter. You can take it to be whatever you want, and I'm taking it to be 1 over n, and I'm taking n to infinity. So, what am I saying? Right, so G string is lambda, well, G string is G square from that equation, which is lambda over n. Lambda is kept constant, and I'm taking n to infinity, so this goes to 0. Okay. I can take lambda to be finite, so in this case, lambda is finite. This is called the foot limit. So on the string theory side, what I have in this limit is that the string coupling constant goes to 0, which means that the strings do not interact with each other. So this is something very nice. This is a simplification. This is the first simplification. Simplification 1. In the limit n goes to infinity, this implies the strings do not talk to each other. Now, on top of this simplification, what else you can do? What you can do is that this is a finite quantity, but you can take it to be very large. So so this is, now I can write this thing as lambda times 4 pi. Okay? So G string is G square n is lambda. So simplification 2 is I'm taking lambda to be very large. Lambda very large means that the curvature of space-time, well, not the curvature, the radius of space-time, curvature is just inverse of this. The radius of space-time, you can think of it as a sphere. The radius of the sphere, measured in string units, becomes very large. So R over LS becomes very large. This means that I can actually, effectively, I can ignore the string excitations. Okay, so this is the same limit that I was talking about. LS goes to almost, well, it's the same thing as keeping this constant, sending LS to 0, or you can keep LS constant, send R to infinity, whatever. But in this limit, only point-like excitations survive. Point-like excitations of string theory survive. That are just the graviton. You know what they are. I told you already. The graviton, the Unique field, the dilaton, etc. In our case, the most important one is G. So this is the second simplification. So in the end, what I have here is the following. So I have this AdS CFT duality, which was very general, gives rise to a duality between large and SU and gauge theory, which equals GR, just general relativity, because string is completely decoupled, and you are left with just GR on AdS times this y. Okay. So this is the simplification. And I will be talking about this. So in the last half an hour, I will present some calculations of, for example, correlation functions or two-point functions in gauge theory from AdS. Any questions? So before that, I just want to take, I want to write a different form of this AdS5 metric, which is more useful. Well, it is the same thing, but it is sometimes it is more useful to do calculations. So first of all, I don't worry about this vector, this S5 vector, because S5 is a compact space. So if you think of some kind of some excitation, some gravitational excitation living on 10 dimensions, some part of it is some part of it is a compact space. What you can do is you can just decompose. You can make like Fourier decomposition, just like you do in both with the spherical coordinates, like the spherical functions y, etc. And that will correspond to infinite number of particles living on this space. So you will have an infinite dimensional expansion. So somewhere I'm saying that if you have a field that this lives in 10 dimensions, so it will depend on R, it will depend on T, it will depend on this x3, xy, z, and it will depend on these angles here that I collectively by this omega phi. But then you can make an expansion by this you have to make a spherical decomposition. So you can make a spherical decomposition in 5-dimensional sphere. It is a little bit more complicated than what we have in 3 dimensions. In 2-dimensional sphere, you have 6 different integers. On omega phi, I have to sum over all of them. But this part will only depend on this 5-dimensional AdS5 part. And so a field living in 10 dimensions, after you spherically decompose on the compact dimension, this is called Kaluza-Glenn reduction sometimes. So this gives rise to infinite number of different fields living on AdS5. But this is what I will do. I will just ignore this part. I will consider that. So I will look at infinitely different fields on AdS5, but I will just pick up one of them and see what it corresponds from the field theory side. Okay, so imagine that I did this decomposition already, and I can ignore this part. This part is important sometimes because not for the application that I'm talking about. So I'm interested in AdS. So now I can get rid of all the rest. And I rewrite this metric, AdS metric, in a different form by just a simple change of variables. I call R over R. I define it as 1 over C. Okay. If you do this, then this equals 1 over Z squared dZ squared plus dx3 squared minus d squared. because r is like 1 over z, so you have 1 over z squared here, you take the square, which is 1 over z to 4, 1 over r squared is like z squared upstairs, so this is 1 over z to 4, this is z squared upstairs, this is 1 over z squared, times z squared, and this is 1 over z squared, and which is here. This is the change of variables, and alright. So now this, I will just use this version. This is the metric that I will use on AdS space. AdS space has a boundary. It's at this point where say z equals 0. You see at z equals 0, the way you measure length becomes infinity. So this, you cannot go beyond this point. It corresponds to a boundary. Z equals 0 is a boundary. And at z equals infinity, it looks like the entire space shrinks down to a point, and it looks like a singularity. This is just an artifact of this representation. So in AdS space, usually it doesn't have a singularity, but in this way of representing it, there is an artificial singularity. So this is the boundary, and we have to deal with that singularity. Okay? It is sometimes called Wonker horizon. I'm just writing the name, it doesn't important what it's called. It's just a singularity where at z goes to infinity, this entire space brings down to 0. Okay, so let's see. What can we do? Yeah, so let's look at how the particles fluctuate on the space. So suppose that I have this AdS5 space, and I want to consider how a scalar field moves on this AdS5 space. So I have to derive the equation of motion for the scalar fields on AdS5, and then solve it, and see what that implies for the gauge inside. Action for scalar field on a curved background. This action for scalar. Following, like there's some coefficients which I don't care. Square root of g. This is a curved space-time. So I have to write down the invariant volume form. It's a high-dimensional space-time that I'm having here. The x I will denote by x, all the coordinates that I have here. There. And then I have kinetic term for the scalar field, d mu phi, g mu nu. I have to contract all of the indices with the metric, otherwise it's not going to be covariant. Plus, say I have an m squared, y squared over 2. Plus you can have additional terms. But if I'm interested in the propagator of the scalar field, this is what I will do now. Propagator. I don't care about these terms. So there may be interaction terms. Okay, so this is the action for a scalar field. So let's derive the propagator. So to derive the propagator, what you have to do is to derive the equation of motion for phi. So that you can do easily by just fluctuating d phi. So the fluctuation of the action, scalar action, about the Lagrangian, will be proportional to del phi times something. Let's define what something is. So if you take the fluctuation, there's a del phi here, there's a del phi here, the 1 2 here. So, well, they are symmetric, so this one over 2 factor cancels out. I have a delta phi, this derivative acting on the delta phi. I just don't want this derivative, so I just integrate by parts, take it here. So what I obtain here is a derivative d mu acting on square root of minus g and acting on all the rest of the quantities. You understand what I have a delta phi here, I just integrate by parts. So it's just the derivative of everything minus the derivative of the rest. The derivative of the rest equals the derivative of this, the derivative of that, and the derivative of this. So I collectively write it as g mu d mu phi. Plus I have this term that just gives rise to square phi times square root. This should be 0, so this is the equation of motion. So the equation of motion, Euler Lagrange equation, is just d mu square root of g d mu then mu phi plus square root. This is for an arbitrary metric. This is the equation of motion for a scalar field on an arbitrary curve background. So what I want to do now is to do it to see what this is on AdS background. So on the AdS background, what you get is as follows. So this derivative, only when this is z, it is not trivial. When it's not z, you can move it here. Right, so this you can write as, so let me divide mu into two parts, mu, z, and the rest. The rest I will denote as, so this this part, let me denote it by x0, x in general. Okay, so this dt is x0, this is x1, x2, x3, so this is xi. Let me call x. So I have what I have from there is that when mu is z, I have, okay, so what is the metric? The metric is like this. The matrix is here, it is 1 over z squared, and then it's 1 over z squared everywhere. When it's t, only there's a minus sign, all the rest is plus. This is r, this is t, this is x, y, z, and the rest are 0. So this is the matrix. The metric. This is the inverse metric, which is just given by essentially just inverting this. Okay. So what I have there then is this dz of okay. So before doing that, I also have this determinant. The determinant of the metric is just essentially the determinant of this thing. In 5 dimensions, it's just 1 over z to 10. I take the square root, so it's 1 over z to 5. Okay. So I have z to minus 5. I forgot to put the square root of g here. There was the square root of g there, I can put it back here. 1 over the square root of g. Z to 5, easy of z to 5. So this inverse metric is for zz component, the rest are 0. So we have z squared, okay, and dz of 5 plus m squared 5 plus the case when this mu is not z, but it's just one of these xi's. So in that case, there's some Doppler effect going on, right? When I talk, when I move. Can you detect that? So this, when this mu is not z, even it is I, it just the metric only depends on z, it doesn't depend on the other coordinates. So I can move this back in here. So what I will have then is, and the square root of g's will cancel out. I will have z squared box in 4 dimensions. Okay, so this box is just the number operator in 4 dimensions. This is that I. So whatever notation you want to use, that I acting on phi equals 0. Now what I can do is I can fully decompose. I can write phi field that depends on C and the other coordinate xi as some previous notation. I will call it phi of Z times each ik dot x. This is the creative composition. I have to sum all these different components, but I'm just picking up one component. Say one component with momentum k. If I do this here, this will bring down the factor of k squared. Okay, so this k squared will be like minus k0 squared plus ki squared. So in that case, what we have is m squared plus k squared d squared phi plus this complicated thing that is essentially just 2z. Minus 3, so there's minus 3z, minus 3. This is minus 3, minus 4. Phi. Easy phi. Plus z cubed, this is minus 3. So this minus 3 times z to minus 4, that becomes z. And then we have this acting on that, gives z squared, dz squared phi. This is 0. And I want to see how this, so this is the value equation, second order differential equation for the scalar field. What I can do now is to see how it behaves near the boundary. The boundary is, remember, z equals 0. I can try to solve this equation near z equals 0. And near z equals 0, you can make an unsatisfactory solution. Suppose that z goes like, phi goes like z to some delta, some power delta plus some corrections. Plug that in. And take the limit z goes to 0. This will not be very important. This will be an important term, and the rest will be important. And in the end, what you will find is the following. So in the first term, you will get m squared d delta. Second, this can be neglected. The second term will be minus 3 delta times z delta. The third one will be plus delta minus 1 z delta 0. And get rid of all these z deltas. And you get an equation for delta in terms of m squared. But you get, in general, this I did for 4 dimensions, but I will write down the equation for d dimensions. In d dimensions, this will be replaced by essentially d minus 1, and the equation right, this is for 4 dimensions, when d equals 4. So this is the AdS metric for in d plus 1 dimensions. Say. So this is d minus 1, and the equation that I get for m squared, sorry, for delta This is a quadratic equation for delta. You will have two different roots. One of them will be d over 2 plus minus 1 over 2. One of them will be the plus sign, one of them will be the minus sign, d squared over 4 plus m squared. So this is the solution for delta, for this power of the scalar field near the boundary. Why is this important? Well, first of all, it tells me two things. That this is not well defined. The propagation of the scalar field on an AdS space is not well defined when this quantity is negative. But it means that the propagation of the scalar field is well defined still n squared when the mass of the scalar field can be negative. Like a tachyon, m squared can be negative. But it should be larger than minus d squared over 4. So this is a peculiar property of AdS space, that the scalar fields, some massive scalar fields, their mass can be negative, but it doesn't mean that there's a tachyon or there's a ghost kind of mode. This is something very peculiar. So this is called the Friedman Loeffler bound AdS space. Good. And there are two different modes. What to do with these modes? So I can give it as an exercise that you will never solve. So I will give the exercise anyway. Just state it. You can calculate the norm of the scalar field. So if I make this decomposition like this, by k times e to the kx, whatever, you can look at how the energy goes like d phi squared. This diverges in one case, it doesn't diverge in the other case. So if you make the decomposition, so from here I will get a z. It's downstairs, so z minus 5. From here, well, I will get z squared upstairs, and then the z epsilon by z squared times this phi of x. So what did I replace this thing by? In general, it can be just a phi of x squared. So if I look at now in the composed version, if I look at the norm of this quantity, it will be given by this integral. And this integral diverges in the case of delta minus. It doesn't diverge in the case of delta plus. Okay, so delta plus is normalizable. Delta minus is non-normalizable. Now let's finally come to the corresponding situation in the field theory side. Field theory, the fact that there's a scalar field that I put on my AdS space that diverges towards the boundary means that I am changing the asymptotic conditions, the asymptotic rules of the game, the asymptotic conditions of the space of the theory. So if I look at the delta minus case, the asymptotics, the boundary conditions are modified. So this is like a singular case. So it changes the theory on the boundary. The plus case doesn't. So what is the theory of the boundary? The claim, what? So the claim, the conjecture of AdS CFT is that I have this AdS space that you can think of some space, some boundary. So this is the boundary z equals 0. This is the interior. But there's a boundary. So the claim of AdS CFT duality is that the first of all, I conjectured that this n equals 4 superiorness is related to this gravity on AdS space. And now the claim is that the n equals 4 superiorness theory is living on this boundary of AdS. So this is the holographic correspondence. So this is the n equals 4 superiorness theory living on the boundary. So now if you consider a propagation of a mode, of a scalar field, for example, it changes the asymptotic boundary behavior. This should correspond of changing the theory on the boundary. So remember, the theory on the boundary was n equals 4 superiorness theory. Now I have to change it. How do you change it? You just add a source term, for example. So you write down a source, phi 0 z, well, phi 0 x. X denotes the coordinates on the boundary, the field theory coordinates, times some operator. Okay, so this operator should have some dimension delta. It is this case delta minus. Oops, sorry. This has a dimension delta plus. Sorry. Right. So this is that case. So and this is the claim. And in the other case, when you have delta plus, and well, this is the minus case. So this is the minus case. And the plus case is just, you have exactly the same theory, n equals 4 superiorness. You don't change the Lagrangian, you don't change the asymptotic behavior of the theory, but instead what you have is some vets, for example. This operator O delta acquires a vet. You change the vacuum of the theory. Okay, so in the last 5 minutes, I will just write down the general formula that is relating these operators and the fields phi in AdS space, and just tell you how to calculate correlation functions by solving this differential equation that we already solved. I will just first write it down and then I will explain. So suppose that I want to calculate an endpoint function on superiorness theory, some operator O. Okay. I want to calculate the endpoint function of this operator O. This I can calculate from the generating function. Okay, so from the expectation value of E2, you getting equal integral of D4x. I should turn on some source, couple it to this operator O. I can calculate this from that by just taking n derivatives. Right? So this will be just del phi 0 x 1, del phi 0 x n of this object, let's call it z of z, and then divided by z, and then take the limit. If the limit phi 0 goes to 0, this will give me that. This equals that. Up to some factors of I. So the claim of AdS CFT is the following. This object, well, we know that n equals 4 superiorness here with this deformation on the boundary equals the AdS, the gravitational physics on AdS space with some scalar field turned on, because the scalar field corresponds to deforming the boundary behavior of the metric, so of the theory. So the claim then is that this equals the exponential of the gravitational action, GR action. Okay, so this is scalar action that I wrote down in the curved space of this field phi xc with the boundary condition. As you go to the boundaries, it goes to 0, this goes to phi 0. Okay. I know that this is complicated, but this is this equation has been checked in many different cases and it works perfectly well. And well, I try to give some motivation for it. And well, the real motivation comes from the fact that you just do calculations and you see that it works perfectly. And so the idea, well, how do you find what kind of field? If you give me an operator in conformal field theories, you specify the operators in their conformal dimensions. So this is called the scaling dimension, lambda. This tells you how it scales, how the operator scales under scale transformations. I wrote down the scale transformation in plus. So if I take an operator called delta, if I change x to x times lambda, this is the scale transformation. I rescale my coordinates, then it is a 2-point component. Lambda, then this should change delta times delta times all, roughly speaking. So this is how, in a conformal field theory, this is a parameterization of different kind of operators that you have. And if you want to do the same calculation of a correlation function, whatever, or an endpoint function in the AdS space, what you have to do is to find a scalar operator. If this is a scalar operator, then the corresponding field should be a scalar field. And if this has a scaling dimension delta, then I just arose that relationship, but I had this relationship between delta and the mass. Okay. If you have a scaling dimension delta, then you should specify, first of all, you should take the correct delta that corresponds to deforming the boundary, okay, delta minus, which is delta minus. And then you solve this equation for m. Then you look at how this field phi with mass m, you look at this propagation equation, and from that you take this propagation equation. Then this gives you the solution, and you insert that solution into this action, the scalar action, that gives you this right hand side. That equals that. It's a function of this phi 0. And from that you can derive the correlation functions. And if you then do that calculation, you see that you arrive at the 2-point functions, for example, for an operator of x itself in a conformal field here. This case like the constant here, x minus y over 2 delta. And you can show that this is the case. So I didn't have time to show it, but let me write down some references to finish with. So there's a big review by Maldacena and others. This is where you can find everything here. There's another review which I like. It's a brief one. My thesis advisor. This guy was my advisor. (0201253). where you can find the calculation of these correlation functions in more detail. So this lecture was just supposed to be an introduction. So yeah. All right. So let me finish here.